Hi, everyone. Welcome back to the grad student seminar. Today, our speaker is Kolomatski, and they will be introducing us to type theory today.
Thanks for having me. Okay, so let's start the talk. I'm going to start with an example that I pulled from my logic notes, and this is perhaps my favorite example. I did not realize the example would work as well when I first came up with it, and then you'll see what happened. So in my logic notes, I, near the beginning, quoted the following passage from a 1973 new math book. Let us look into a modern mathematics classroom. The teacher asks, why is 2 plus 3 equal to 3 plus 2? Unhesitatingly, the students reply, because both equal 5. No, reproves the teacher. The correct answer is because the commutative law of addition holds. So then, in my logic notes, I was trying to push towards a certain viewpoint of addition. And I began asking the question, what are the least helpful ways to answer the question? What is 5 plus 13? And one such way is to just say, well, 5 plus 13 is what? A number. That's really getting into the weeds of what the word is. You can also say that 5 plus 13 is just 5 plus 13, or 13 plus 5.
Ross?
Yep.
We're supposed to be seeing things?
Oh, you're not seeing things.
It seems like
That
it's
is bad.
the first slide.
Do you see things now?
We see Spotify.
Ah,
There you go. Okay, yeah, see it now.
Okay. Yes, good. Multiple slides, they're changing?
That's good, yeah.
Okay. Right. So we are looking at least helpful ways to answer what is 5 plus 13? A number. 5 plus 13 is 5 plus 13. 5 plus 13 is 13 plus 5. 5 plus 13 is 7 plus 11. Another way to add them up. Well, okay, let's try and ask a more pointed question. What is the value of 5 plus 13? This shouldn't let you get away with answers like this. Well, one of my students said the value of 5 plus 13 is learning how to add. Another creative use of the word is. You could also say the value of 5 plus 13 is the value of 5 plus 13, and so on. So it really seems the problem is the word is. And in order to do this, we'll modify the question. We'll in fact stop making it a question. We'll issue an order. Just evaluate 5 plus 13. And I don't think there's any ways to go about this. So there's this notion of values when it comes to addition and this process of evaluation. Now, how I actually began my notes is discussing numbers. And I said we're going to go back to a kindergarten model of numbers. And so what do you learn in kindergarten about the notion of numbers? And I actually looked up the Ontario education standards for this. Well, numbers are definite ways to answer questions of the form, how many apples are there in this basket? Now, how would you answer this question? You'd go to your basket, you'd start removing apples, and then you'd start with 0, increment every time you removed an apple, and then you get to some number. And this process is known as counting. This is how you answer the question. How many apples are there in a basket? You count. And the key point is that you can count up to any number starting from 0, where by number, I mean natural number. Now, what if you have 2 baskets of apples? How do you count the apples in 2 baskets? Without, of course, dumping one basket into the other and then counting. Well, one answer is that you first count the first basket, then you start at that number that you got to instead of 0, and start counting the second basket from that point. And this is known as addition. So this is the kindergarten apple model of numbers. Now, in this model, what does 2 plus 3 equal to 3 plus 2 mean? Well, I think that it clearly corresponds to the idea that if you choose to count one basket before the other basket or the other basket before the first basket, you'll get the same result as to the total number of apples that there are in these two baskets. This suggests perhaps that the meaning in general of commutativity is that for all concrete numbers n and m, the expressions n plus m and m plus n have the same value. And so in my notes, I really wrote the following offhand lines. These are throwaway lines in the truest sense. In our setting, this law cannot be stated without reference to evaluation, referring to commutativity. However, the equality 5 plus 13 equals to 13 plus 5 may be seen through direct evaluation without invoking commutativity. In other words, Johnny was right. Now you see where this is going to go. There's only one way it can go. It can't be made formal, it must be made formal. So suppose that we have an implementation of mathematics on a computer. I do have one. And plus com is some proof of the commutativity of addition. Now, if you have a book like Bourbaki set theory, or let's say Bourbaki analysis, you hypothetically know that you can take any proposition there and you can expand the definitions recursively until you get down to the primitives in the volume on set theory. You just copy every single lemma that's used directly into the proof. This is something that's prohibitively complicated that you'd never actually do by hand, but you hypothetically know that it's possible to rewrite any proof in analysis in terms of just the logical primitives. So this is what I'm going to do with this proof. I'm going to write a single wall of text expansion of every single definition of the proof. And what do I get? I get this. This expression right here is the statement because the commutative law of addition holds, written out in pure logical primitives. Now, of course, I can take the statements because the commutative law of addition holds, and I can specialize it to the numbers 2 and 3 written in this successor notation. And what do I get? It can only be one thing. Reflexivity 5, because both equal 5. What a computer has just done is that it has just evaluated a wall of text function and scientifically proven that Johnny was right. And that is my starting example. Now, moving on, let's discuss group theory. So in the ambient context of group theory, I can write the following expression. GH times H inverse parenthesized like this. I rebracket by associativity. I cancel the inverses, and then I use the right unit law. And by the way, this example is taken from my advisor's paper, The Logic of Space. So the question is, where does this computation take place? Now, one answer that you can give to this question is in any group. But another answer, arguably a better answer, is that it takes place in the free group on two generators, specifically generated by symbols G and H. Now, consider the free group on two generators. What is the universal property of this? Well, what property does it satisfy? Well, if you have any other group and you specify where the elements G and H get sent, then that uniquely extends to a group homomorphism from the free group to the group G. So in other words, the data of a group homomorphism from the free group to any group G is just determined by two elements in the group G. And then if we look at the expressions that we had before, something like G times H inverse parenthesized this way equals GE is an equality of definite elements in FGH. You can write elements as strings of the symbols GH, their formal inverses, and the identity. And the universal property lets us interpret G and H as being elements in any group. So that's what connects the free group on two generators, this specific initiality universal property, to any other group that we may care about. Now, I'm going to say that we can think of G and H as a syntactic formal system, and I'm going to specify what I mean by this in some way. So we can perform arguments to the group essentially in this specific group, essentially by pushing symbols. And then we get an interpretation of these arguments in any groups. This is essentially the semantics of the arguments, and that's furnished by the universal property. Now, notice that you can't prove many general statements about groups in the free group because very little happens in the free group. It's very free. There are syntactic models which have a single relation imposed. You can take quotients, such as quotienting by the normal subgroup generated by the relation g squared equals h cubed. That's sort of a presented initial object. It's initial in groups with two marked elements satisfying that relation. So now I said that this is a formal system. What do I mean by saying that it's a formal system? Well, we can give a construction of this group. Now, if we looked at the argument that we had before, we had explicit associativity invoking, we had full parenthesization. And so one construction that just directly matches that is to say that elements are classes of fully parenthesized products in the 5 symbols, G, H, their formal inverses, and the identity. Now, I say classes because they're generated by some relations. The relations are unit laws, associativity, inverses, and canceling inverses. And then the product is very easy to give. For the product, if everything's fully parenthesized, you just concatenate 2 expressions and then you put outermost parentheses. In the next slide, I won't write the outermost parentheses, though. And notice that this definition doesn't just give a construction of a group. What it actually gives is a syntax for writing arguments about this group, and for a deductive system for deriving equalities. So to give an example, let's say I define conjugation by G, which is one of the generators, to be this expression. I have to fully parenthesize it because I'm saying that my elements are classes of fully parenthesized elements. And then suppose I want to prove that this conjugation operation is a group homomorphism. So in this model, where I have full parenthesization and where I have to rebracket associativity every single time, what does the proof look like, given the rules that I provided when constructing this object? Well, it looks like this. So, I mean, what do you expect? You have to rebracket associativity. It's not going to look nice. We should burn this with fire. That's what we should do. So what is the correct way to construct the free group on 2 generators? Well,
Paris, I have a question. What was wrong with the brackets?
So the idea is that the way that we constructed this group is that saying that they're classes generated by relations, that description gives us a way of arguing. And the issue with this way of arguing is that the arguments that this is a group homomorphism shouldn't be this hard to prove. You shouldn't want to rebracket associativity every single time that you prove that this is a group homomorphism, say. And even worse, this argument only applies given that G is a single symbol, one of the generators. If G were in fact conjugation by something consisting of 3 symbols, this argument would not generalize and it would be bigger. So this isn't you would never, if you were just doing math in the background, write this full arguments to show that conjugation is a group homomorphism, right? I mean, this is pretty bad as a way of proving things. It's not easy to prove it. I mean, it's sort of direct. It's what you expect. It's what you get when you have to rebracket associativity. But the point is that I'm going to make is that if you actually choose a better construction, you will get much nicer proofs. Does that make sense?
By hard and you should burn it, you mean as in computing time or as in human would grasp it?
We should not use this model. We should definitely construct the group in a correct way. So let me show you the correct construction now. So elements are reduced words, which are now with completely unparenthesized words in GH and their inverses, such that there are no loci of cancellation. So you can't have G followed by G inverse in a reduced word. Also, there is, for the word that has no symbols, we just denoted the empty word by E as the identity. Otherwise, in all other non-identity words, they're just words in the four symbols GH, G inverse, and H inverse. Now, what is the product in this group? They're not classes, they're just reduced words. The product is that you concatenate two words, and then in their place where they meet, there might be opportunities to cancel. So you keep canceling until you get down to a reduced word. But that's not enough. We also prove a meta-theoretic property that if you have any unreduced word, in other words, a word with possibly multiple places to cancel, not just a word that's made by putting together two reduced words where there's going to be at most one place to cancel at each step. This is any number of sites of cancellation. Then you prove, in order to get nice properties, that no matter which order you choose to cancel pairs in, this process will always terminate, and it will terminate in a specific reduced word that is independent of the sequence of cancellations made. And that's called a normal form of word. So in order to give a good construction, you show this property that's, and what does this property imply? This property implies, for example, associativity of the product, where you can just put three words together and then cancel in any order. And it's the same as though you were handling all the cancellations at the first locus or at the second locus first. Now, another nice property is that if you have any words without indeterminates, by indeterminates, I mean variables that stand for something, we'd have those in arguments. But if you have two concrete words, you can test for equality by reducing them to their normal forms and checking whether their normal forms are equal. That's a nice property of this construction that you didn't have in the property of just equivalent classes. Here, if you have two members, you can test whether they're in the same class. This construction requires a lot more work than the previous one, but what do we get from it? Well, let's say we're going back to the same proof. We want to prove that conjugation is a homomorphism. Then the proof looks like this. You put the words together. Again, since A stance is now an indeterminate, A might end in G or begin with G. Sorry, A might begin with G inverse or end with G. So there might be cancellations, but the property that we showed about any reduction sequence giving the same results means that this argument actually goes through. We've taken this specific syntactic construction and we've proven enough properties so that this argument makes sense and this argument formally translates into an argument about any group. So the way that you construct your syntactic object matters. In a better syntactic model, you get much nicer arguments and you get a much more usable formal system. So now in this construction, we constructed an object freely generated by two elements in the category of groups. And we saw that the choice of syntax can significantly affect the utility of using the system. Now, what is type theory in a sense? Well, one of the goals of type theory, is to provide a convenient syntax for free objects in any mathematical universe whatsoever. And what we're going to see in today's talk is, in fact, such a syntax for monoidal categories. And this syntax is actually going to have equivalent expressive power to string diagrams. But that's just a tangential thing. I don't actually see how it's a syntax for monoidal categories. You can read Schulman's notes on categorical logic to see that. So let me just check how I am for time. Oh, I'm doing very well for time. Somehow making slides means that I give myself a license to go quickly. By the way, are there any questions so far? So these two examples were my type examples.
Oh, can I ask a question?
Yeah.
Maybe maybe I'm not so what is the meaning of convenient syntax? You mean like do you want to find like a effective generator of groups? Like for example, if you have a homotopy group, and can you find the effective
Right.
generators? I don't know the meaning of convenient syntax.
So there are several properties that you can have from your syntax, and some of them are suggested from the previous ones. In terms of being able to find, for example, if you have some presentation of a homotopy group and you want to know the order of the group, so you want to find the isomorphism class, well, you can't magically solve non-computability of group theory in a sense. The parts of group theory that are computable, you can set it up so that you have syntax that does, for example, compute numbers automatically. One property, this is a bit of hype, is that the mathematics is going to be entirely constructive, which means, for example, that it's going to have a property called canonicity. So, for example, canonicity says that if you have any closed term of Nat type, in other words, you have some expression in your theory that defines a concrete number, then the fact that the entire theory is constructive means that this expression is essentially a program for computing that number. An example that my advisor gave in a talk is, for example, you can define the degree of a map. And I'm sure that all of us have at some point stared at a commutative diagram, and there's some number in the commutative diagram. Is it multiplication by 2? Is it multiplication by 1? I want to know this. Well, if you have a constructive definition of degree, and you have a constructive definition of that map, then the problem of wondering what the degree is completely solved, because you can just ask the system to evaluate that number and it will give you that number. And that is a very strong meta-theoretic property, canonicity, that you get when you construct everything exactly right. And that was, I guess, suggested by this property before about, for example, you can check for equality by checking just for definitional equality of normal forms of elements. And the reduction to the normal form can be done by an algorithm.
Yes.
So that was a very high-end preview. But for example, every single number that you define as an algorithm for computing that number is, you can see it as something that's really desirable from this example of knowing what the degree of any map is, right? Does that make sense?
Yes, yes. Thank you for the answer. Yeah, that sounds interesting. Yes.
Right. So let's get started then. I'm going to show you today the simplest example of a type theory. I'm actually going to fully express it, and you're going to see how type theory connects to logic and how you write proofs in type theory. So first off, we're going to talk about propositional logic. And propositional logic has a syntax. The syntax is defined by a grammar. I'm going to give the grammar right here. Now, X stands for any propositional variable. So we're going to assume that we have an infinite list of variables, which I'm going to, for propositional variables, denote by capital letters, A, B, C, etc. Well, a propositional variable is an atomic logical statement. So for example, SBU is in Stony Brook is a statement. And then let's imagine that that statement doesn't have any other internal structure. So these just stand for some logical statements that we can't look further into them. They stand variables for some logical statements. So a logical formula is any propositional variable, or if you have two logical formulas, you can construct one formula implies the other formula, one formula and the other formula, the other for the one formula or the other formula, or not a formula. So let me quickly show you what this syntax means on a whiteboard here. Do you see screen right now?
Yes.
Okay. So for example, I can define a grammar for natural numbers. A natural number is either Z, or a natural number is a successor of a natural number. So nat appears twice here, once on the left-hand side of the equation and once on the right-hand side of the equation, but it's not an equation, it's a grammar. And for example, if t appears twice, this appearance of t is completely disconnected from this appearance of t. These aren't called variables, these are called non-terminals, but that's just a technical point. So what does the grammar for natural numbers say? Well, one thing that it says is that z is a natural number. So z is a natural number. Now, since I know that z is a natural number, the second rule says that if I have any natural number, I can form the successor of that natural number, and that is also a natural number, right? Now,
What do you mean by
one
a
way that you
successor?
can view.
Sorry.
So right now, this grammar is just defining strings of symbols. I am going to define a collection of expressions. The expressions look like z, s of z, s of z, right? So for example, I can write down the string foo, or 1 plus 2, right? These are strings of symbols that are not in the language defined by this grammar. Of all strings, there are a collection of distinguished strings. Maybe I should fully parenthesize this. And that's the strings distinguished by this grammar are strings of the form z, or s of z, or s of z, in general z, or the successor of any other natural number. So do you see the pattern in these strings, right? Let me show you one other way to view it. You can actually view anything constructed as a grammar. It's actually not that good to view them as strings. The better way is to view them as trees. So for example, if I have z, that's a natural number, I can use a constructor to construct a tree whose root is s. And then if I have that tree, I can use that tree as a child to another tree whose root is also s. So you can think of the grammar as defining a class of trees where z nodes are leaves and s nodes have one child. And these are rooted trees with ancestor-descendant relationships. Then in the grammar for propositional formulas, and by the way, in this talk, we'll focus on the segment of the logic that only has implication in it. So first off, the fact that x is in blue means that it's a non-terminal. So for example, it stands for any propositional variable. So A is a logical formula, B is a logical formula. And then since both of those are logical formulas, you can form the logical formula A implies B. Now you can also form the logical formula A implies B implies C. And as a tree, this looks like implies as a root. Then here I have A. Then here I have a descendant which has implies as a root, and then B and C. So if I look at the structure of this, it's an implication where the left-hand side is A and the right-hand side is B implies C. Does that make sense? Now, another thing that I can do is by convention, implication is right associative. So what I mean by this is that instead of writing A implies B implies C, this will just A B implies C. Okay, so that's just a primer on syntax and how to read grammars. Are we back on the slides? Right. Does anyone have any questions?
Can I ask a silly question?
Yeah, go ahead.
Is it? This is a not may not relate to math. Is this type theory related to linguistics? Is it possible to apply to linguistics?
Oh, well, the notion of grammars arose from linguistics. So right now we're talking about syntax, right? This is just syntactical specification. So yes, linguistics is also very much about syntax, and linguistic definitely uses the type of grammar that you're seeing right here is called a Brachis normal form grammar. It's a general grammar for context-free languages. So for example, you can have in sentence diagrams, a noun phrase is something, something, and then you draw trees for how to drive full sentences, right?
Yes. And
so that's exactly the same thing that's going on here. Now
also
I can tell, go ahead.
Yeah, so you mean like type theory is like kind of this idea is from syntax in linguistics?
Well, type theory, it has a syntax. The syntax is a small part of type theory. So right now, I'm just defining something that mathematicians care about just as much. For example, you can have the formula A or not A. That's the law of excluded middle. And we sort of have an idea of what that means. So we also have, these are the syntax of logical formulas. Mathematicians have logical formulas as well. So this grammar is not distinctly a part of type theory. It's also a part of classical mathematics.
Yeah. Thank you. Yes.
No worries. Okay, and so I'm saying that right now in this talk, we'll just focus on the first two cases of this grammar. So propositional variables and implication. Now, I decided to cut the section where I talk about the notion of truth of a formula, but I can say something about that very, very quickly. So, for example, the formula A implies A should be true. And I'm going to go over this very quickly and verbally. You can look at the propositional variables that occur in the formula, and you can consider each variable as either being true or false. And then if you make an assignment of each variable to a true value, that is called the valuation. Now, a valuation extends over formulas using the logical connectives using truth tables. And that defines a valuation on all logical formulas inductively. Because the grammar constructs formulas inductively, you define the valuation, I guess, recursively. Now, we say that a formula is true if and only if under all valuations it becomes true. That is called a Boolean interpretation of truth. And what I really want to emphasize, that's, I guess, what you're taught in Math 100. That's the classical logical viewpoint on this, is that we're going to throw away truth. We don't care about truth. We only care about provability. And we're not going to discuss what it means for a formula to be true at any other point in this talk. We're only going to focus on the notion of proof. So what is proof? Well, let's just see. Colloquially, if we want to prove A implies B, we often assume A and prove B, right? If something, then something. How do you prove it? Suppose first something. And the assumption A may be used somewhere in the proof. So somehow after you assume A, the background state of what you're allowed to do changes. And so we need some way to keep track of the assumptions that we've made. And we'll do this using a context. So a context is just going to be a list of assumptions, a list of things that we assumed to hold. And what we'd like to do is we'd like to make statements of the form in context gamma t, where t is some logical formula defined by the grammar. We've defined what all possible logical formulas are. In some contexts, t is provable. This is going to be called a provability judgment. And we're going to denote this provability judgment using something called a sequence. And so this is the V dash symbol. It's also called a turnstile. So gamma turnstile t, that is an expression which is read as in context gamma t is provable. Any questions? Right. So the short form is that when you see a symbol like this, that symbol expression denotes the statement in context gamma T is provable. So here are some examples of sequence. I can assume, for example, A implies B and A. And then in the context where I've assumed A implies B and A, I'm going to say that B is provable. You can also make no assumptions, and then nothing appears to the left of the turnstile. So for example, from no assumptions, I claim that A implies B implies A is provable. And remember, I said that implication is, right associative. I don't know if I wrote right associative, I might have made a mistake, but I mean right associative. So this is the same as A implies, and then the right-hand side of the implication is B implies A. So here are some examples of sequence. Now, what is proof then? Proof is defined by rules which say that some judgments, I'm going to call them judgments, the sequence are judgments. I mean, sequence are a particular form of judgment. Judgment is a more general word. But they say that some judgment follows from 0 or more other judgments. So here is an example of the first proof rule. This is called the assumption rule. This says that if I've assumed T, then T is provable. That certainly makes sense, right? The notation here is that if I have a context and that I write comma T, I mean the context with the additional assumption of T. The next proof rule says that if I've assumed T as an additional assumption to the context gamma, and from it I'm able to prove W, then I'm able to prove T implies W in the original context. But that's a bad way to read the rule. The better way to read the rule would be from the bottom up. In order to prove T implies W, you need to show that assuming T, you can prove W. Then the next rule is modus ponens, implication elimination. If I can prove T implies W and I can prove T, then I can prove W. Those are going to be the 3 proof rules. This is going to be our entire proof system for the remainder of this talk. So it's very important that we're all on the same page about these rules. And if anything's unclear, then I would be very grateful if you'd ask a question. Anyone?
What is the purpose of the comma?
Right. So you can see on the slide before, for example, in the first example, my context was A implies B, comma A. So if I have multiple assumptions, I'll separate them by a comma in the context. Now, gamma is just a variable, a meta variable, standing for any context. So it can be several assumptions. Now, if I want to add another assumption to that context, then I do so by adding a comma. Now, gamma comma T just means any context in which T has been assumed. And then you can see that, for example, in the implication introduction rule, the context changes from the conclusion and the assumption. So in particular, in proving T implies W, you assume T. And what the context does is it keeps track of this assumption. It simplifies this statement. It removes the T implies. So it becomes a strictly less complicated expression, but the context changes, and the context is there to keep track of the assumption. So this just means I've added the assumption T to the context gamma. Does that make sense?
Got it. Thank you.
Right. Good. Anyone else? Okay. So one rule that says if you know something, you know something. That's really it. The other rule tells us how to prove implications, and this is called the implication introduction rule because the conclusion has an implication. And the other rule is called the implication elimination rule, because if you assume an implication, it tells you how you can use an implication. How can I use the information that T implies W? Well, If I also know T, then I can use both pieces of information to know W. And remember that the judgments say that something is provable. So in this case, if assuming T you can prove W, then you can prove T implies W. Now we can take these proof rules and we can chain them to form a tree-like structure. And in some tree-like structures, we'll derive the bottom judgment from scratch. So here's an example. Suppose I want to prove A implies B implies A. Then I assume A, and I want to prove B implies A. Then I assume B, so now I've assumed A and B, and I want to prove A. But I've already assumed A, right? So since A is in my context, I can justify that A is provable using the assumption rule. I'm going to assume that my contexts are unordered. So A appears before the comma, but acceptable abuse of notation in an hour talk, right? And the easiest way to read these trees is from the bottom up, actually. Then you see what rule is applied in each instance. And the key property about this tree is that the leaves of the tree do not have any judgments in them. So this is a derivation of this judgment from absolute scratch. And we say that a proof of a statement is a derivation tree that derives the judgment from scratch. So that is what we mean by a proof of a statement. We conflate proofs with these proof trees. Any questions? Okay, I need to go a bit quicker. So here's another example. A implies B implies B. This is an example where we're actually going to use implication elimination. I assume A implies B. And now since I've assumed both of those, I have A implies B, I have A, I use the elimination, I use the implication, that gives me B. And then I pull the assumptions back in and form functions. Not form functions, form implications. Okay, now we're going to discuss what does a proof mean. We're not satisfied with this perspective of proof trees. We want to do constructive mathematics and we want to view proofs as mathematical objects. So there's something called the Brouwer-Hoiting-Kolmogorov interpretation. This is the constructive interpretation of proof. The constructive interpretation of proof says that a proof of T implies W is a construction that, when given a proof of T, produces a proof of W. What does it mean to prove T implies W? Well, it means that if you have some proof of T, you can get some proof of W. Now, we're going to take the statement very literally. And what a construction that when given something produces something looks like a function between what and what. We're going to identify the logical statement T with the space of proofs of T. The space, as opposed to the collection, is more of a homotopy type theory terminology, but I do that, so I'm going to say the space of proofs of T. And then in fact, a proof of T implies W is nothing but a function from T to W, where by T and W, I mean the spaces of proofs of T and the space of proofs of W. So now what about the implication elimination? Well, if I have a proof of T implies W and I have a proof of T, then I can get a proof where I think of a proof as a concrete mathematical object by evaluating the function, by applying the function to the inputs. And so what we need is a language for describing functions and applications. And this language is, of course, going to be defined with a syntax given by a grammar. But I'm going to have a lot more examples this time. So this language is called simply typed lambda calculus. To begin with, there are going to be the types, which are just going to be the same grammar that we had before about implications. But the interesting thing is the terms now. A term is either a variable. Notice this is a capital X and this is a lowercase x. So we're going to assume that all of these variables are distinct from all of these variables. Or it's an expression of the form lambda x in t dot t, or t applied to t. So I am going to say a bit more about this in a second. So the capital X stands for, instead of calling them propositional variables, now I'll call them atomic types. They're types that have no further structure. And the lowercase variable stands for a variable, which I'll denote with X, Y, Z lowercase letters. And we view these two syntactic categories as distinct. Now, here are the names that I'm giving them. T is the grammar of types. Capital T is the grammar of types. Little t is the grammar of terms. The three cases of a term are a variable, an abstraction, or an application. An abstraction is a way to form a function. In mathematics, we'd write x, then we'd write the maps to arrow, and then we'd write the body of the function. Here, we write the variable. This t is the body of the function, and this colon t specifies the domain of the function. And then we write function application just by concatenating two terms. So let me give you some examples. Okay, but before I do, let me just say what the important thing about the slide is. We have a notion of terms, and a term is either a variable, a function formation, which I call an abstraction, or a function application, duly called an application. So here are my examples of terms. A variable is a term. The grammar says that a variable is a term, so a variable is a term. My variables are x, y, z. Now I can take a variable and I can apply it to a variable. F and A are variables, and I can consider the application of F on A. This is a variable applied to a variable. I can also write a function, lambda x in A dot x. And this looks like the identity function. So this is lambda. It says it's a function on the parameter is going to be the variable x. The variable x ranges over A, and the body of the function is just x. And this x refers to the bound x right here. Here's another function, point evaluation at A. Lambda f ranging over A to B, and the body of the function is f applied to A. And this function is point evaluation at A. Here's another function, lambda f in A, f applied to f. I call this self-evaluation. Here's another example, double application, taking a function f from A to A, a term in A, and then applying f to A twice. And you can also have applications where the first thing is a lambda. So this looks like the identity function applied to A. Here are some examples of terms that are defined by the grammar on this page. Now, where are types coming into this? Well, if I look at the identity function, this says that the input ranges over terms of type A, and then the body of the function is just x, and this x refers to something of type A. So this suggests that the function takes something of type A and produces something of type A. And so that suggests that this function should have a type itself, and that type itself should be A to A. It's a function from A to A. Now, let's consider this expression right here, the double evaluation function. Well, if I have f from A to A, and I have A, and I apply f to A, I've given something of type A to A, a term of type A, I get something of type A, and then I do the same thing again. So this function takes something from A to A, it takes something of type A, and then it produces something of type A. And that function really should have a well-defined type, right? Now, if I just consider the term x alone, there's no context for its typing. What does x mean? I don't know what type x is. So I can't make a typing judgment there because I don't have enough information. Similarly, in the point evaluation at A function, it would make sense if A had type A, although I have nothing that says that, so I still can't make a typing judgment. There isn't enough information. Now, what about the self-application function, where I applied f to f? Well, f was of type A. A is not a function type. A is just an atomic type, so this shouldn't make sense. F should not be a function according to these types, so that this does not look like a term in which the typing makes sense. In fact, you can show that there is no type T such that this composition is sensical. So right now, I've said that I've hinted at the fact that there's a notion of typing of terms and that some terms have a type, some terms do not. So what are the rules for typing? What are the rules? We now need to give some rules to make this notion formal. Right, but before that, I need to say what is a typing judgment? So first off, here, the only time that we're giving type information explicitly in a term is on lambdas. They're binders on X and they give type information about X. But the grammar for this has variables. In other words, we're only going to be given type information on variables, not on more complicated expressions. And we need to keep a way to keep track of these assumptions. That's going to be a context. And a context isn't just going to be formulas. Now, it's not just going to be types. It's going to be bindings of variables to types. So the context is now going to contain the information of what type certain variables are. And we'd like to make judgments of the form in context gamma, T has type T. And this is going to be called the typing judgment. That's the title of this talk, the typing judgment. And I'm going to write it like this. It looks like the judgment that we had before, but it's going to be gamma turnstile T has type T. And this is read as in context gamma, T has type T. So what are the typing rules for making these judgments? The typing rules are going to be, as predictably, rules that say that one typing judgment follows from 0 or more typing judgments. The first rule is, how do you type variables? Well, the only way that you can type a variable is if you already know what type that variable has, and that would only happen if the variable is already in your context. Now, how do you type functions? Well, in order to type a function, you assume that the variable has type, the indicated type, and then you try and type the body of the function. How do you type a function application? Well, if the function has type T to W, and the argument has type T, then the application has type W. And so if you think about it, if you just think about functions and function application, and you think of domain range and domain range coinciding for a composition to make sense, then these rules are just that. Now, what's the most important point about these rules? It's that there are 3 different syntactic categories of terms, and each syntactic category of term exactly corresponds to a rule. There is a one-to-one correspondence between rules and syntactic categories. In other words, for example, if I had a judgment where I typed a judgment, I typed an application, then if it's well typed, if there's a way to conclude this judgment, it can only be concluded with the implication elimination rule because it's an application. So here's an example of a typing derivation tree. I'm going to consider this function right here, lambda A to B, F applied to A. I'm going to claim that this has type A implies B implies B. And how did the rules proceed? Well, what type of term is this? It's a lambda, which means that the only rule that I can apply to conclude its typing is an implication introduction rule. So I take the variable, I throw it into the context. I look at the term right here. It's a lambda, which means the only rule that I can use to conclude this is an implication introduction rule. So I throw F into the context. Now I have an application, which means that the only way that I can conclude this typing judgment is using the implication elimination rule. Now I look at both of the factors inside. They're variables. The only way I can conclude them is using the variable rule, which just does a context lookup. So this tree, essentially, if you looked at the line on the bottom, it wrote itself because there's a correspondence between rules and syntactic categories of terms. The rule that you do at each stage, your hands are tied. And that's the really important point, that syntactic categories of terms exactly correspond to proof rules. So what's the key meta theory? The key meta theory is that if you have a term, there is at most one type T, such that T has type T in a given context. Further, for any judgment, there is at most one derivation tree for that judgment. And most importantly, this tree can be computed algorithmically. A computer can do the process that we did before of giving a proof term, reconstructing the proof tree. So the idea is that these proof terms encode proof trees. And so then we get to this duality that we've been hinting at in this talk. And that's the BHK interpretation. What happens is that we identify types with logical formulas, Previously, in the language of types, I said atomic types and arrow types. But then in the language of propositional logic, I had propositional variables and implication. Well, in the duality, we blend these two things together. We think of types as logical formulas, and we think of terms as concrete proofs. And that's why we call them proof terms. A proof is valid if and only if the proof term is well typed. And this idea leads to how proof assistants work. What does a proof assistant do? A proof assistant is given a certain judgment as inputs. Let's say in context gamma, little t has type t. And then given this as input, the proof assistant will either successfully reconstruct the tree, reconstruct the derivation, and accept the judgments, or it'll fail to do so, and it'll gracefully throw an error indicating where type checking fails. Now, generally, we'd ask the proof assistant to verify judgments in an empty context. There are ways to add things into a context. And also, another really important thing about proof assistants is that they can often fill in the blanks. So for example, if we're given this judgment right here, where notice I've dropped the type descriptions off of the variables, it turns out that there's only one way to add type descriptions to make this judgment sensible. And a computer is actually able to work out what the type descriptions on A and F should be. So almost virtually, every single type description that you write is actually redundant. And for a computer, this expression lambda A, lambda F, F applied to A encodes the entire proof tree. So instead of giving that proof tree that we saw before, you could just give this proof term, and proof assistants would be, given this proof term, have enough information to reconstruct the proof tree without any guesswork, just algorithmically and rotely. So now I ask, who win? A grown-ass proof tree or one lambda boy? This is how we were encoding proof trees at the start. Yeah, using this full notation. And if we accept that type descriptions can be inferred from the typing judgment, then this term right here just encodes the proof. Now, okay, so it looks compact, but are there any other benefits that you can get from this viewpoint? And here is where I show you what the benefit is. It's not just about conveniently being able to encode proofs. It's also about a completely different perspective on what proof is. And I call this thinking constructively. And this is an example that I made for my students. So I was trying to explain this to my students and I came up with this example at a certain point. So suppose we're trying to prove the statement A implies B implies C implies A implies B implies A implies C. So remember, it's right associative. So the left-hand side is this, the right-hand side is this, and then the right-hand side internally has the left-hand side of this and the right-hand side of this, etc. So how do I prove the statements? Well, I can actually take this and I can reword it. And I'm going to reword it like this. Suppose you are in some room and you have some coins and there are two vending machines. The first vending machine sells nutcrackers and the second vending machine sells walnuts, but the walnuts are in a shell, right? So the question is how nom? How nom? How do I nom? I want noms. And the answer is absolutely trivial because our brains effortlessly navigate such situations daily. If you have a vending machine with nutcrackers, a vending machine with walnuts, and some money, and you want to eat, you're going to be able to eat. You're not going to sit there thinking for a very long while of how do I eat, right? This is a completely trivial question when it's reworded like this. Does everyone see? Oh, so can someone tell me how would I eat? So in particular, the question is, imagine yourself that you're in this room, you have some coins and you have these two vending machines. One sells nutcrackers and the other sells walnuts. How do you get some food? Anyone?
You buy the nutcracker and the walnut and then use the nutcracker to crack the walnut.
Exactly. And that's direct. So you put a coin in one machine, you put a coin in the other machine, and then you use one output on the other output. Okay, so let's do a translation into types. I'm going to say that A is the type coin, B is the type walnuts, C is the type food. Then a walnut vending machine is something that takes coins and produces walnuts. It has type coin to walnut. A nutcracker takes walnuts and produces food. A nutcracker vending machine takes coins and produces something of type walnuts to food. And so what was the solution? You put a coin in one machine, you put a coin in the other machine, and then you use one thing on the other. And this solution can be encoded in 19 characters like this, assuming that we don't have to write type descriptions, which can be inferred by proof assistance. X, it has type of nutcracker vending machine. Y has type walnut vending machine. Z has type coin. So you take a coin and you use it on the nutcracker vending machine. You take a coin, you use it on the walnut machine, and then you use the nutcracker on the walnut. And this proof term exactly encodes that. And this provides a different constructive perspective about thinking about proofs. So now I'm going to say something very quickly about the other logical connectives. So for the other logical connectives, what happened was that for implication, this BHK interpretation saying that a proof of T implies W is a construction that when given a proof of T produces a proof of W, really you can think about it as that sentence already encodes everything that we did today. This interpretation really suggests that you should have functions for those constructions. And then a pure language for talking about functions and applications is typed lambda calculus. That's just pure functions and applications. I guess untyped lambda calculus would be that, but we're working in a type setting. Now, so similarly, what terms you do, what rules you consider, they follow from their description. And then it's really easy to say what a proof of A and B is. So the BHK interpretation of a proof of A and B is a proof, or of proof of T and W is a proof of T and a proof of W, of course. What is the interpretation of a proof of T or W? Well, it's a proof of T or a proof of W, concretely, constructively. So you can think of then a proof of T and W as a box that has two mathematical objects in them. One is the proof of T, one is the proof of W. And then a proof of T implies T or W, the way I said to my students, is that it's a box that has a slider to two different positions. If you slide it to one position, you can put in a proof of T. If you slide it to the other position, you can put in a proof of W. Now, what about the interpretation for knots? Well, we run into a bit of a problem because we'd like to say a proof of not T is something, something, a proof of T. And that's a bit of an issue because proof of not T should not involve a proof of T. So I leave that as an exercise to you. You definitely can make negation work in type theory, but I'm not going to tell you how to do it. And so that is my talk. All is done.
Okay, let's thank our speaker. And we're a bit over time, so maybe if there's one question from the audience.
May I ask a question, Taras?
Mm-hmm.
It's more of me checking if I understood. So you basically started with some example to show us that how choosing the right rules would make it more efficient for computers to read or to actually check that a proof is correct. Or
more importantly, for humans to write the proofs.
Okay, my question is that how does type theory basically fits with the incompleteness theorem, Gödel's incompleteness theorems, and these type of stuff?
Well, so you certainly can't solve uncomputable problems. And the other idea is that type theory is actually not just a single language. It's a highly modular family of languages. So for example, I just gave you logic with implications alone. Typically, when you think of logic as being something absolute, where of course you have predicate logic, of course you have and, of course you have or. Here I have a logic that only has implication. And then I can add and to it. I can just optionally add and. I can add and, but not and or. I can add or, but not add and. And this way, so originally this was supposed to be a 2-part talk, but my second talk got axed. And there was going to be a really strong point where I was going to go into homotopy type theory in the second talk. And I still hope the second talk is going to be scheduled. But what you would have seen in the second talk is that everything that we've done today actually has secret computational meaning inside of it. All of this is constructive, which means somehow we've justified how these proofs should behave in a computational setting. And each module is actually a constructive interpretation of that specific area of logic. Now, how it fits into Gödel's incompleteness theorem is that logic is not absolute. Logic is small advances, and every single advance that you do, it's justified by giving a constructive interpretation of what you're doing. If there were one absolute logic, then that would be that. Maybe set theory-based math, although we know that that's not the case. There is no absolute logic. Type theory provides essentially a pure way for having constructive interpretations of context, constructive interpretations of some constructs, and providing rules for how those constructs behave. The modularity means that you can make systems of increasing levels of power to suit the logic of your needs. It's a specific initial syntactic model for working in some mathematical universe, and you can make that mathematical universe as complicated as you want. So type theory isn't just a single system, is what I'm saying. And logic is not absolute. And this modularity and the fact that whenever we add something, we fully substantiate it and we fully philosophically consider what this notion is before adding it with exactly the right rules, which when you do so, you have the secret computational interpretation, which, for example, results in things such as every single concrete definition of a number is an algorithm for computing that number. That, of course, means that, for example, if you want orders of a group, you can't solve the group isomorphism problem. That's an unsolvable problem, so you can't give a constructive definition of the rank of a presented group. That at the same time, you can also work non-constructively. You can add rules to type theory that aren't fully substantiated. And if I had my second talk, I'd be able to give you this in more detail. Type theory in general, when you go into predicate logic and when you add higher order logic and higher equalities, it's a syntax for working in infinity categories. So types actually have the structure of infinity groupoids, and we're really launching into syntax for higher categories. The syntax that you just saw today, that's a syntax for monoidal categories. And another such syntax is string diagrams. So in fact, this system of proof rules, it's an equivalent syntax to string diagrams. They prove the same thing about string diagrams when considering monoidal categories with their tensor products. That was a really roundabout answer, but
No,
modularity.
Okay, thanks again, Taras, for the talk. So that concludes the grad student seminar for today, and we hope to see you all next week. So take care.